Hello students, welcome back to the chapter Haloalkanes and Haloarenes of class 12. In this part we are going to learn how to prepare haloarenes from aromatic hydrocarbons. So in the last part we have learned to prepare haloalkanes from alkanes or hydrocarbons. Here we are going to see how to prepare haloarenes from aromatic hydrocarbons. So this is the method. So here we have aromatic hydrocarbon, and from that we have to prepare aromatic haloarenes. So what are the conditions and reagents required for this? So basically two methods are used. First one is electrophilic substitution of aromatic hydrocarbon ring. So electrophilic substitution we will see that in the slides. What does this really mean? The next one is Sandmeyer's reaction. So two types of methods can be adopted in order to fulfill this conversion. So let us see one by one. First one is electrophilic substitution of aromatic hydrocarbon ring. അപ്പം ഇലക്ട്രോഫിലിക് സബ്സ്റ്റിറ്റ്യൂഷൻ എന്താണെന്ന് നമ്മൾ പിന്നീട് കാണും. ഓക്കെ, നമുക്ക് വേണ്ടത് സബ്സ്റ്റിറ്റ്യൂഷൻ റിയാക്ഷൻ ആണ്. ഏതിൻ്റെ? അരോമാറ്റിക് ഹൈഡ്രോകാർബണിൻ്റെ. അരോമാറ്റിക് ഹൈഡ്രോകാർബൺ ഐ ഷുഡ് ഹാവ് ദി സബ്സ്റ്റിറ്റ്യൂഷൻ റിയാക്ഷൻ. സോ ലെറ്റ് us take the basic aromatic hydrocarbon. അതേതാണ്? ബെൻസീൻ. Clear? So benzene substitution എന്ന് പറയുമ്പോൾ what I am expecting, what is the product that I am expecting is, so I must have that benzene ring, and on one carbon there should be the halogen group. So this is called as haloarenes, isn't it? So this is haloarenes. So this is what I want. Aromatic ringum വേണം, അതുമേ halogenum വേണം. If I want that, what are the things I should supply? There must be halogen. ഈ halogen എന്ന് പറഞ്ഞാൽ chlorine or bromine. It is not iodine. Chlorine or bromine ആണ്. Iodine ആണെങ്കിൽ the conditions will differ. So which we will see. The reaction will differ and the reaction will be very slow. So there are certain other conditions for if it is iodine. So this X2 means it can be either chlorine or bromine. And you should also have what we need is a catalyst. Here the catalyst is iron, which is a Lewis acid. So instead of iron you can use any other Lewis acid like aluminium chloride or bromide. Iron chloride or bromide can be used as the catalyst. So here just I took one Lewis acid as a catalyst, and the reaction should be carried out in the dark. Clear? So in the presence of iron, if there is X2, if there is light, imagine that there is no darkness, there is light. Light undu ennu karudha. What happens? You know, X2 will attack the double bond of benzene. Double bond ne break ചെയ്ത് if X is entering into benzene, then it is not substitution, it will be addition reaction. What we need is a substitution reaction. So what happens if I am giving all these things? What happens is I will get the substitution of either chlorine or bromine. So how to understand the mechanism? Lewis acid will polarize bond in X2. So it will polarize bond in X2. So what happens? This Lewis acid will polarize the bond in X2, which I will draw here. So I have XX bond. This will polarize Lewis acid, being an electron deficient group. Is an electron deficient group, so it has a positive charge. It will break this bond and it will take away the negative X. Positive X will move and attack the electrophilic center. Electrophilic center means electron rich center. Clear? So if he is, let's assume that this bond pair is taken away by this X. This bond pair is taken away by this X. So he will become X minus like this. And this will become X plus. That's what Lewis acid will polarize bond in X2 into X plus and X minus. Electrophile means electron loving X plus isn't it? So this will be electron loving. So let's assume this is the electron loving group. Electron loving group will try to look for electron, and when he approaches the benzene, he will see that carbon on the benzene is rich in electron, so he will attack that electron. That's how it got the name electrophilic substitution. Clear? Now if you are allowing the reaction to continue, what happens is more X will come and attack on this, which you will see again later in the chapter. Okay, so if I want chlorobenzene from benzene, I must treat this for some time, then you will get chlorobenzene. Clear? So what happens to the H here? The remaining H, so it is a substitution. X has substituted an H here. H will go with the other X, which is negative in charge. So X plus will attack here, and H that is coming out will, H plus that is coming out will go with X. And you will also get the byproduct as, so the byproduct is HX along with this, which is not written here. So it is written in this statement. So this is for understanding, not for studying. Clear? അപ്പം ഇത്രയും കാര്യങ്ങൾ നമ്മൾ ശ്രദ്ധിക്കണം. So these are the requirements for the reaction. You should have a Lewis acid, which is initiating the breakage of X and attachment to the benzene ring. Clear? And the reaction must be carried out in dark. Why? Otherwise it will be an addition reaction. It will break the double bond and it will start getting attached here like this, but the resulting thing will not be an aromatic haloarene. It will not be an haloarene. It will be a cyclohexane with a X on it. So it will be an addition reaction. So darkness is important. Clear? So that's the first part of this reaction. Next, this is the basic. Benzene means is the basic aromatic hydrocarbon. Next we will look into the next type of aromatic hydrocarbon, that is toluene. So next higher aromatic hydrocarbon is toluene. So when I am going to have an electrophilic substitution on toluene, I can follow the same steps. What are that? I will have halogen here. So halogen is again chlorine and bromine. Then I have a Lewis acid, and I should do it in darkness. Why I should do this in darkness? Otherwise X2 will go substitution onto the alkyl chain. Clear? Onto the methyl carbon. It will substitute it there. So in order to avoid that, I must have darkness. And also, since Lewis acid is there, this compound will try to make an addition reaction here. In order to block that, I should have darkness. Clear? So what happens? Let us see. Here it is the true meaning of electrophilic substitution is coming in this type of reaction. So X will split into X plus and X minus, as we see as we saw in the last slide. X2 will split into 2, that is X plus and X minus, and X plus will attack the electrophilic center on this compound. Electrophilic center on this compound. So which are the electrophilic centers on toluene? We will see the results first. From the results you will be able to understand it. So the electrophilic centers are, from the results itself it's clear. It is ortho position and para position. Which are the ortho and para position? It is the second carbon is the ortho position and fourth carbon is the para position. Clear? Why are these ortho and para positions electrophilic? So let us see that. It is due to the so again X means Cl and bromine, and it is due to the resonance. Ortho and para positions are electrophilic centers due to resonance. It's for your understanding. So if you are drawing the resonating suches of toluene, so I have toluene. I have just shown its structure. CH3 group is attached to benzene. So what happens is, initially this bond will shift towards this single bond here, and which will end up in a double, becomes a double bond, and H plus is going out. Now these two bonds cannot stand here together on same carbon atom. Two double bonds cannot be afforded on same carbon atom, so this double bond will move towards to the next carbon. Clear? Will move to the next carbon. So what will happen then? We will see that carbon will become anionic or an electrophilic center. So the ortho carbon is now an electrophilic center. Now carbon cannot is not stable as an anion, so he will release his electron to the next bond. So we will see bond. Once it is released, it will become double bond. Double bondum തൊട്ടപ്പുറത്തെ കാർബണും ഒരു double bondum. So this carbon cannot afford two double bonds. So he will move on to the next carbon. This double bond will move on to the, while this carbon move on to this bond will move on to the next carbon. So what happens? Let us see. So this has become a double bond, you can see here, and this double bond has shifted to this carbon. So now which carbon is electrophilic now? This is the ortho carbon, sorry, para carbon. So here ortho carbon is electrophilic, this is para carbon that is electrophilic. Now this again will move on to the next bond, moved. So this double bond can't stay here, he will move on to the next carbon. So what happens? You will get again on the ortho carbon. So this is again ortho carbon to this carbon, becomes an electrophilic center. Clear? He will move on to the next one, and this bond will move on to hydrogen back again. So what happens? You will get the structure back, but in this figure, all the double bonds in this figure is now single bond here, and also the double bond here are single bond here. So these are the resonating structures. If you are looking into the resonating structures, ortho positionilum para positionilumana what? Electrophilic centers. That's the reason in the product, while the product formed, X plus is attacking ortho position and para position. Remember one more thing. Halogen, while he attacks, he can attack both these carbons simultaneously. ഇതിപ്പം നമുക്ക് ഒരു മോളിക്യൂളുമേ ഓർത്തോ അറ്റാക്ക് ചെയ്താൽ പിന്നെ ആ മോളിക്യൂളുമേ പാരാമ അറ്റാക്ക് ചെയ്യുന്നില്ല. ഹീസ് അറ്റാക്കിംഗ് പാരാ പൊസിഷൻ ഓൺ അനദർ മോളിക്യൂൾ. That's the peculiarity of this group here. So here, who is contributing the electron? It is CH3, isn't it? CH3 is contributing the electron and initiating the resonance. അങ്ങനെ CH3 initiate ചെയ്ത് കഴിയുമ്പം he is getting electron rich center, he is getting electron rich center, isn't it? അപ്പം CH3 ആണ് initiate ചെയ്യുന്നത്. Actually this group attached to the benzene is initiating the resonance and making ortho and para positions electron rich. But CH3 is a weak we can say ortho and para directing group. You can say ortho and para directing means he weakly allows the electrons to move, whereas there are certain other groups which they will make that movement quite stronger. And അപ്പം ആ കേസിൽ ഓർത്തോ പൊസിഷനിലും പാരാ പൊസിഷനിലും electron density will be very high. If the electron density is very high in ortho and para on the same molecule itself, അതേ മോളിക്യൂൾമ തന്നെ ഒരേ മോളിക്യൂൾമ തന്നെ എക്സിന് ഇവിടെയും അറ്റാച്ച് ചെയ്യാം ഇവിടെയും അറ്റാച്ച് ചെയ്യാം. But in our case it is toluene, it is weakly directed. So what happens? What happens is, if on one molecule there is an ortho substitution, on the same molecule there will be no para substitution. Para substitution will be taking place on another molecule. Now in the product what you will see is, you will have ortho and chloro, a mixture which will be in excess, which is the major product among ortho and para, which is the major product. This is what we are going to see in the coming slide. So I guess it is clear why it is ortho and para, because you have two electrophilic centers. One is in ortho position and the other para position. In the next slide we are going to see which is the major product. So we have ortho-halotoluene and para-halotoluene. By looking into the structure, it is very clear that XII CH3, they are very much in the close proximity, so there will be a big strain between them to occupy in this constrained positions, whereas E parallel CH3 and X is far away, so they can be relaxed, there is no strain. So which one will they prefer while they forming product? So from in this reaction, which one they need to have a relaxed position? Clear? That is para halotoluene. So both the products will be there, but majority of product will be para halotoluenes, and ortho halotoluene will be minor in product, but still we need to separate them. Clear? So in order to separate, how to separate them? I need to separate para halotoluene and ortho halotoluene from the reaction mixture, from the product mixture. How to do this? So if you're looking into the symmetry, there is no symmetry here. Here you can see that clearly there is a symmetry, like both the substitutions are in the opposite direction. So there is a symmetry. Because of that, there is a large difference in the melting point of ortho and para isomers. So this, because of its symmetry, can be neatly arranged inside the solid. So inside the solid there will be a neat arrangement, whereas in this case the arrangement will not be that structured. Because of that, melting point of para isomer will be very high. So para isomer have higher melting point due to the symmetry, and we can separate them based on this difference in the melting point. Ortho and para isomers can be easily separated based on the differences in the melting point. Okay, so it's how to separate them. Electrophilic substitution reaction can be carried out directly with chlorine and bromine. We have said that already, right? So in the electrophilic substitution, we were using halogens. Halogens was either chlorine or bromine, but not iodine. Why? Because when you are using iodine, the iodine is reversible. We have studied iodine is reversible. So what happens? Reaction with iodine are reversible in nature and require presence of oxidizing agents like HNO3 or iodic acid to oxidize HI formed during the iodination. So during iodination, HI will be formed. If there is these acids like HNO3 and iodic acid, they will take away this one. So if they can take away this one, then fine, you can use iodine. But you cannot use iodine directly without the presence. So you should have some oxidizing agents like HNO3 or iodic acid if you want to use iodine. Clear? Next, fluorine is also not possible. Fluoro compounds are not prepared electrophilic substitution because fluorine is also, why? Because due to high reactivity of fluorine, direct fluorination can be dangerous and explosive. Clear? So this method is not also used for direct fluorination because they are dangerous and explosive. Clear? So these are the two things that you have to keep in mind. In electrophilic substitution, what you will get directly is chloro and bromo arenes, whereas for iodo you need to have this oxidizing agents in it, and fluorine is not possible. The other methods we will learn later. Okay, so first thing is over, electrophilic substitution of aromatic. So we have seen this electrophilic substitution for benzene as well as for toluene. Next, what we are going to do is, or see, is Sandmeyer's reaction. So Sandmeyer's reaction starts with aniline. The original Sandmeyer's reaction starts with aniline, but aniline is not a aromatic hydrocarbon, isn't it? So the reaction starts with aniline. You know the structure of aniline, you might have learned it, but it is not an aromatic hydrocarbon. So if you want to categorize the Sandmeyer's reaction under aromatic hydrocarbon, I should first know this method. Aniline is first produced from benzene. So first I have to learn how aniline is produced from benzene. Benzene ആദ്യം എങ്ങനെ aniline ഉണ്ടാക്കുന്നു? Clear? Sandmeyer's reaction aniline നിന്നാണ് സ്റ്റാർട്ട് ചെയ്യുന്നത്. So first I should know how to produce aniline from benzene. If I know that, then the reaction is starting from benzene. then it is an aromatic hydrocarbon ring. So let us see that. Aniline is first produced from benzene through nitration and followed by reduction. So let us see that reaction first. Aniline from benzene. So we have benzene. If benzene is undergoing nitration, എന്ന് പറയുമ്പം സാധാരണ generally, there are exceptional cases, but generally nitration is a mixture of concentrated HNO3 and concentrated H2SO4. HNO3യുടെയും H2SO4യുടെയും ഒരു മിക്സ്ചറാണ് നൈട്രേഷന് യൂസ് ചെയ്യുക. So a mixture like this, concentrated H2SO4 and concentrated HNO3, and slightly heating it. So that is nitration. So if the benzene is undergoing a nitration, what happens? A nitro group is attached onto benzene. That is called nitrobenzene. Clear? But what we need is aniline. So we have NO here. Instead of NO, I must have H, which means that I have to reduce this compound to aniline. So nitrobenzene, if you are treating with, you might have learned the common reagents and catalysts that are used for reduction is hydrogen and palladium. Clear? Catalytic hydrogenation. This is the simplest method of reduction. നമ്മൾ സാധാരണ റിഡക്ഷൻ നിങ്ങൾ ലോവർ ക്ലാസ്സുകളിൽ തൊട്ട് പഠിച്ചിട്ടുള്ളതാണ്. റിഡക്ഷൻ, കാറ്റലറ്റിക് ഹൈഡ്രോജനേഷൻ, കാറ്റലറ്റിക് റിഡക്ഷൻ എന്ന് പറഞ്ഞാൽ എന്താണ്? ഹൈഡ്രജൻ ഇൻ ദി പ്രസൻസ് ഓഫ് പല്ലേഡിയം, പ്ലാറ്റിനം, നിക്കൽ. Any method you can use. If you reduce it, what happen? Oxygen will be gone and hydrogen will be there. So you will get aniline. So this is the compound aniline. Sandmeyer's reaction actually starts from here, but we are categorizing this reaction under aromatic hydrocarbon. So due to that reason, first we have to show how benzene is being converted into aniline. Clear? So aniline is obtained from benzene in a two-step process. First one is nitration. എപ്പോഴും നമ്മൾ ഓർത്തിരിക്കേണ്ട കാര്യം ഓർഗാനിക് കെമിസ്ട്രിയിൽ. സോ ദീസ് ആർ ദി ഇമ്പോർട്ടൻറ്റ് ഫാക്ട്സ് ദാറ്റ് യു ഓൾവേസ് ട്രൈ ടു റിമെമ്പർ. നൈട്രേഷൻ എന്ന് പറഞ്ഞാൽ 95% കേസുകളിലും ഏത് മിക്സ്ചറാണ് നമ്മൾ യൂസ് ചെയ്യുക? മിക്സ്ചർ ഓഫ് H2SO4 and HNO3. So in 95% of cases you will use this mixture. So the nitrobenzene so formed has to be reduced. Reduction, in many cases we can use simple reduction method. Simple reduction, if it is not possible only, then we will use special reducing agents. Clear? So here it is a special, it is not a special reduction, it is a simple reduction. So we use H2 plus, means catalytic hydrogenation, catalyst as palladium. If I am using it, I will get aniline out of it. Clear? Next, how I can use aniline in order to have haloarenes. Haloarenes ഉണ്ടാക്കാനാണ് ഞാൻ എന്ത് യൂസ് ചെയ്യുന്ന? aniline in Sandmeyer's reaction. So that's Sandmeyer's reaction. The starting material is aniline, as I said. So aniline is first treated with sodium nitrate HX at 0.5 degrees centigrade. So what I need is a special acid here. The name of the acid is, so I will write it. The name of the acid is HNO2. What is the name? Can you recollect the name of the acid which you have learned in class 11? This HNO2. The name of the acid is nitrous acid. Nitrous acid. നമ്മൾ nitric acid പഠിച്ചിട്ടുണ്ട്. What is the formula of nitric acid? Nitric acid is HNO3. Clear? So this is another acid, lower oxidation state ഉള്ള നൈട്രജന്റെ nitrous acid. ഇത് unstable ആണ്. This acid is unstable at a room temperature. So in order to make this acid, I have to make it whenever I need it. ഈ ആസിഡിന്റെ സ്റ്റെബിലിറ്റി ഇല്ലാത്ത കാരണം എനിക്ക് ഈ ആസിഡ് വേണമെങ്കിൽ ഞാൻ എന്ത് ചെയ്യണം? അപ്പം ഉണ്ടാക്കണം. That how can I make it? I take a salt of that acid, that is sodium nitrite. NO2 group is nitrite, sodium nitrite and mix it with HX. With HX. ഏതെങ്കിലും ഒരു ഹാലിക് ആസിഡായിട്ട് മിക്സ് ചെയ്യാം. So for example HCl. And you should be careful, it is unstable at higher temperature. So I have to keep it at the lower temperature. So this mixture will now provide nitrous acid. And this nitrous acid is added into aniline. What happens? Let us see. So aniline will give benzene disonium halide. This compound is called benzene disonium halide. If it is chloride that I used here, I will get chloride. If it is bromide, then I will get bromide. So benzene disonium halide. Clear? On the top of what it was NH2 there. Now it will be N2. We know that what N2 is. N2 is nitrogen. And that nitrogen is attached onto the top. Since nitrogen is sharing its lone pair, it will get a positive charge. And that positive charge will attract the X minus on this from this supplied halic acid. Clear? So it's benzene disonium halide. And what is the structure of benzene disonium halide? It's a very important compound in chemistry. Clear? And that has, instead of NH2, we have N2, nitrogen attached here. Is attached using lone pair. And because it is attached using lone pair, this compound is highly unstable. Very, very unstable compound. So this instability is also, that's one reason why we have taken there is the carrying out this reaction at low temperature. So two reasons. One is to keep this acid stable, and the other one is to increase the stability of benzene disonium halide. Clear? From here I have to split the reaction into two. So I have got benzene disonium chloride. We will see the structure of this reaction of this compound later. From here I will split the reaction. One is Cu2X2. So here if X must be S can be either chlorine or bromine. So I am using cuprous halide, either bromine or chlorine. If I am using this, what happens is the entire thing will go away and here X will come. So let us see. You can see here this N2 which is unstable will fly off as N2 gas, and instead of that, whatever I am using here, either chlorine or bromine, it will come here. So it can be either chlorine or bromine. If I am using cuprous chloride, it will be chlorobenzene. If I am using cuprous bromide, then it is bromobenzene, and nitrogen will fly away. Now I can make chloro and bromo like this. How to make iodine? For that I just have to add Ki, potassium iodide. What happens? Iodine will come and nitrogen will fly away. Clear? So this is Sandmeyer's reaction. I started with aniline. I have to add nitrous acid. So nitrous acid, to obtain nitrous acid, I have to add sodium nitrate. It's a salt plus halic acid, which will be treated at very low temperatures, approximately equal to 0 and 4 or 5. This is called a diazotization reaction, and I will get benzene disonium halide. So once in board exam they have asked for this reaction, diazotization reaction, which means that into aniline I am adding this and making the compound into a benzene disonium halide. Clear? This benzene disonium halide, upon treatment with cuprous halide, if it is chlorine and bromine, you will get chloro or bromo compound, and if it is iodine, it is more reactive, so you don't have to add this expensive thing. You can add simply potassium iodide, which is easily available in most of the labs. So potassium iodide, you will get iodobenzene. In both cases nitrogen is liberated because this nitrogen here attached here. So we will see the structure of that. So you can see unstable structure where we have benzene, and on the top of the benzene you have nitrogen attached with its lone pair. Since it has given its lone pair, it has a positive charge, and X will attach to the nitrogen. So the nitrogen attached to the benzene is having positive charge. Must be able to remember that. Clear. Nitrogen attached to the benzene ring is having positive charge. Clear. So that's all about the Sandmeyer's reaction. Now we are making a summary of all the reactions that we saw in the preparation of haloarenes from aromatic hydrocarbons. First one was the direct substitution on benzene, electrophilic substitution, as we discussed. X2 plus iron in the dark can be any Lewis acid, you will get halobenzene. Use looking into this, try to draw the structure and try to reproduce what you have learned. So halobenzene, halo means it can be either chlorine or bromine. If I want iodo, I should add additional thing, that is okay, toluene we will see first. Toluene, the same things, you will get two products, orthohalotoluene and para-halotoluene. Clear. In this case, in the first case, coming back to this first case, it is halobenzene that I am initially getting. Later you will see that in the reaction, you will see that if I am keeping this reaction for some more time, you will get additional products, which we will see later. Okay, so the toluene, I will get two products, orthohalotoluene, para, and para will be the major product and can be separated by the differences in their melting point. Clear. So these compounds, why it is ortho and para directed? Because they are the electrophilic centers for toluene. Clear. Next, if I want iodo, then iodine must be supplemented with either of the oxidizing HNO3 or HiO4, that is iodic acid, nitric acid or iodic acid. I will get orthoiodotoluene and para-iodotoluene. Clear. Now Sandmeyer's reaction, for Sandmeyer's requires aniline. So benzene is first nitrated to nitrobenzene, which is reduced to aniline. This aniline is treated with nitrous acid to give benzene disonium chloride. So nitrous acid is mixture of NaNO2 plus HX plus 0.5 chlorine. You must write this because there is no reagent called nitrous acid readily available. Whenever you need nitrous acid, you must make it by mixing these things, these conditions, and mixing the reagents. So you'll get benzene disonium chloride, disonium salt, and this disonium salt is treated with Cu2X2 to get either chlorobenzene or bromobenzene, or you can treat with potassium iodide to get iodobenzene. So these are the reactions which we learned in this part. Study well. Okay, try always, as I said, always try to write and study. Okay, thank you.